Uh, Top of today's resistance and resistivity. It's not going to be overly long, but okay. Resistance and resistivity. All right, so resistance is, essentially just what it sounds like when we're talking about electricity. It is a impedance, which is actually another word for resistance. It's an impedance of the flow of current through a wire. So this is meant to represent a wire or a current carrying conductor. It's easiest just to make it a cylinder, all right? And so to understand resistance, we just have to think about what's inside here. So if this is metal, which it would be in general. It might be a semiconductor, but we'll talk about metal, like a true conductor. What you end up having is you have all of your atoms, arranged inside of here, and they have their inner shells, your inner shell electrons, which are bound or locked in closed shells. And then outside of that, they have their free electrons, or their valence shell electrons, right? So depending on the metal, they may have more or they may have less electrons in their outer shell. Now these electrons are not bound electrons, okay? These electrons are the ones that are able to flow. So if we provide a voltage across here, okay, what you end up getting is electrons moving from an area of high potential, or if you want to think about it, you could think that there's a more negative charge over here, and therefore they move away from that area towards positive, and they're attracted over here. Okay, that's probably the simplest way to think about it. In reality, there's a field across here, and the electrons move in response to the electric field. Now, they are impeded by the fact that there's matter in the way, right? They can't just freely flow. They run into all of these atoms that are kind of in their way. And that is essentially the source of resistance inside there. It's like the physical resistance between these electrons and the atoms that are in it. How exactly you can overcome this in a superconductor, I'm not sure. I know it has to be really cold, so I assume it's got something to do with how much these guys are vibrating, right? The more they vibrate, the higher resistance tends to be. Not in all materials, but yeah, you can kind of think of it like a bit like friction. But what we're really interested in here is how does this affect the overall resistance? So there's a couple things to consider, okay? When we're talking about how much resistance a piece of wire will have. First is the type of material. Okay, so different materials have different natural like impedances or resistances. The unit for dealing with that is called the ohm meter. Okay. So this is the resistivity of the material. Okay. I'll just give a couple of samples. So copper would have a resistivity of, let's see here, 1.7 times 10 to the negative 8 ohm meters. And let's just do another one for interest's sake. Let's try like iron, something like a little less, a little bit poorer of a conductor. And then maybe we'll try something that is a insulator. So let's say Teflon. Somewhere, I don't have an exact number, but okay. So what you'd have is you'd have a range from a good conductor, and I believe, if I'm not mistaken, copper is the best conductor. Actually, sorry, silver. Silver is a little bit better. It's 1.6 times 10 to the negative 8, but a good conductor. And then you'd have a long range all the way down to a good insulator. And you can find tables with these values just laid out in them. Okay, so just threw up kind of a large uh, table of these things. Uh, Resistance changes with temperature too. That's something to keep in mind. So these resistivity tables are good for a certain temperature range. The ones I showed you were for 20 degrees, which is room temperature. So you can have a look and see where your favorite metal sits. There's a misconception that gold is the best of all conductors. That's not actually true. Silver is, but the reason you see gold associated often with electronics is because it doesn't tarnish. So if you have gold-plated terminals, gold does not, corrode in the air, and so those terminals will make good electrical contact, for many, many years, maybe forever. Okay, so the second thing, the material is important, but the second thing that's important when considering this is the area or thickness of the wire. Okay, so if you have like a little narrow gauge wire, and the wire is measured in this strange system called gauge in North America. I assume there's a metric equivalent to gauge, but we often use AWG, so American Wire Gauge, where the higher the number, the narrower the wire. So we've got that kind of system going on. But anyway, the point is, a narrower wire will have more resistance than a fatter wire. Okay, so less resistance on the fatter wire. Why? As I understand it, the electrons that are traveling have a skin effect, right? Essentially, they move to the outsides as far as they can on these wires, right? They try to concentrate as far away from one another as they can. So they call this the skinning effect. So the current is actually carried along more or less the surface of the wire rather than right down the center of it. So, I mean, the larger the area of the wire, I guess the larger the surface area around the wire, and therefore the lower the resistance. There's probably more to it than that. There probably is some current leaking down the middle, but this concept of skinning effect, I know it occurs. You also see it in, say, like a lightning strike, where if your body's wet and you get struck by lightning, the majority of the current will travel through your outer wet coating, through your clothes and so on, rather than through your body. Not saying that you're going to survive a lightning strike just because you're wet, but some people have survived, and that's the main reason why, because most of the current would have gone around it rather than through their body. Okay, so there's a skinning effect. That's something to be aware of. But really the net result is a fatter wire, a wire with a larger, if you want, cross-sectional area, will offer less resistance per given length. Yes, exactly. And then the third one is length, length of wire. Um, Obviously, the more length that the current has to be pushed through, the more overall resistance you're going to have. Okay, so we could say then, if we want to write this down, resistance is proportional to the length, and resistance is inversely proportional to the area. Okay, larger area, lower resistance, longer length, higher resistance. And what links them together to actually get a resistance value on here is P, the resistivity. So what do we get out of all of this knowledge? We get this little formula right here. The resistance of a wire is going to be equal to its resistivity times its length divided by its cross-sectional area, all in meters, right? So let's see how we can use it. 4 meter It's not really a P. It's a, I don't know what symbol it is. It's like a, it's this symbol. So it's not a true P. It's, yeah, I think it must be a Greek letter, but I don't know what it's called. Actually, I realize I do know. This is a lowercase rho. R-H-O. Rho. Okay, anyways, a 4 meter long copper wire has a gauge. We're going to go on gauge and we're going to convert it to metric. So what gauge wire do you want to have? That's really fat wire, isn't it? That's like house wire. Yeah. This is going to be low. Let's make it long then. Let's make it longer because that's going to have such low resistance. It's not even going to be fun. Let's make it like 100 meters. That's probably not even long enough. Let's make it like 250 meters. Let's make it a kilometer. I'm making it 1,000 meters. Why not? Okay. Has a gauge of 14 on the American wire gauge. Predict the resistance of the wire. Okay, so we had to go to a handy lookup chart, and we found out that 14 AWG is equal to 2.08 millimeters squared in terms of cross-sectional area. Okay, so that's actually giving you the full area of the wire if you were to cut it and look at it end on. Sometimes in a question you might be given the radius of the wire and then you have to convert right to its cross-sectional area. So you cannot use something like radius or diameter directly. You have to you have to make sure you have to watch for that. Okay. Cross-sectional area, if you cut it and you look at the end of it. Okay, so this is the wire cut in half and I'm looking down it, right? 2.08 millimeters squared. Okay, so remember our units, right, are in terms of meters. So we actually have to convert this to meters. So how are we going to do that? How many square millimeters in a meter? Do you remember? Here's how you do it. Here's a box. Say this box is 1 meter on a side, so it's 1 square meter. Well, 1 meter is the equivalent of 1,000 millimeters. So each side is 1,000 millimeters. We know 1,000 times 1,000 is. I think you need to redo your math. I'm pretty sure it's a million millimeters. Okay? Yeah, exactly. So we've got 2.08 times 10 to the negative 6 meters squared. All right, so and resistance of this E L A. Okay, so we've got copper, so 1.7 times 10 to the negative 8 ohm meters times a length of 1,000 meters divided by 2.08 times 10 to the negative 6 meters squared. So on that, just doing that math, you get about 8.2 ohms. So like, is that a lot? I guess is the question. Well, it depends, right? Uh, like, let's say that you have, I don't know, let's say that you have 500 volts across that, for instance. Okay, so here's your 1 kilometer of 14 gauge wire. What if you're trying to carry 500 volts here? What kind of current are you going to get here, right? So we know this, V equals IR. So I over R. So first we'll check what kind of current we have going through here, and then we'll check what kind of power loss you're going to have from here, right? Let's go 61. Let's round it. Let's get 61 amps going through here, right? So how much power are you losing as your current travels through here, right? You're gonna have some loss due to heat, right? So we know this. Okay, so P equals IV. 61 amps times 500 volts. We're talking here like 3,000? Yeah, sorry, wrong order of magnitude there. Why isn't this one right? No, roughly 30 kilowatts of lost energy. So, if you're a power company and you're trying to deliver power to people, you have to consider this concept. Like, there's lots of power lines running everywhere. Um, how do they deal with this usually? What's a way to deal with this? Yes, number one, make the wire thicker. Absolutely. You make the wire thicker, that lowers resistance and it lowers power loss. Another interesting thing is you run it as DC voltage at very low current. So one way to transfer electricity a long way is run it over DC. That seems to decrease power loss, but if you amp this up to like incredibly high voltages, right, but at very low currents, the power losses decrease quite significantly. So you might find things like, you know, 20 megavolt uh, power lines, right, that are running like extremely low current just to minimize the per kilometer power losses that you would get if you were running skinny wire at low voltage, right? Right. So high voltage, essentially what they'll do is the power companies will convert to very, very high voltage but low current for long distance delivery. And then at your house, you have low voltage but high current, right? Often a house will have like a 200 amp breaker, so you can draw 200 amp into the house, but it's at, it's at 110 or 220 depending where you live, right?